In this video, we are going to go over how to solve a definite integral involving U-substitution. And then at the tail end of it, I'm going to go over the significance of even and odd functions in integrals. That one's not a big deal. Neither is this first one. Let's jump. So to evaluate a definite integral, meaning we've got lower and upper bounds or numbers here, essentially what we need to do is we need to also, in terms of doing our normal U-substitution, write these in terms of U. Let's go over that. So first things first, I'm going to let the innermost function equal to U. That's very often going to be the case. Not always. We'll see in the exercises it's not always the case, but often. So the innermost function is x squared minus 1. Oh, and then du is going to be equal to 2x dx. Now, what I don't have here is I don't have a 2x dx. Now I am going to factor out that 6. I'm intentionally leaving these numbers off. You'll see why shortly. I've got an x. And then in here, I already know that this is u cubed. Now, I've got your dx here, right? So x squared minus 1 is u. All right, so we've got that there. I need a 2x dx, so I will multiply by 2. That gives me 2x dx, but then I need to multiply through by 1/2. So nothing new there. Nothing new there. And we'll keep substituting down here. We'll do it in steps. Half of 6 is 3. 2x dx, that is du. Oh, and then you'll get u cubed du. Now, you might be wondering, why did I not put the 1 and 2 here? To be conceptually correct, what we've just done is we just rewrote this function as u cubed. And if you were to graph this out, it doesn't look like something cubed at all, right? It's actually like something to the 6th times x, something to the 7th. Whoa. So it's not something cubed. So we've totally reshaped this function. So we've got to reshape the bounds because what we're doing here is we're finding the area from 1 to 2 in terms of x. But the area, which needs to be the very same area that we're finding here in terms of u, would not be bound from 1 to 2 since we changed the shape of the curve. So we've also got to change the bounds. So some teachers teach keep the 1 and the 2 here, solve this out in terms of x in the end, and then plug in the 1 and 2. If you're taking the AB or the BC exam, you will lose points for that. Conceptually, you must change your bounds in terms of u. So how do we do that? Well, each of these are x values. We want them to be u values. Here's our u translator, if you will. So all you do is you take x equals 1, you plug it in there, right? You just plug your x values into here. So that's u equals, and this is when, you know what I'll do notation-wise? I think it makes a lot more sense. I'll just say when x equals 1, u is going to be equal to 1 squared minus 1, just plugging it in, which is equal to 0. So u is equal to 0. There's your u substitution for that x. When x equals 2, u, which is x squared minus 1, is going to be equal to 2 squared minus 1. All I'm doing is plugging that into the u translator. 2 squared is 4 minus 1 is 3. Oh, so now I've got my two u values completely substituted. And now all I have to do is rock this thing out like normal. So this is going to be equal to 3 times u to the 4th over 4, normal anti-differentiation. And because we don't need to rewrite this in terms of x, because we're just looking for one definite value, these are u values. I can plug them directly into my answer with the first fundamental theorem of calculus. So you've got 3/4 u to the 4th. So that's going to be times 3 to the 4th minus 3/4 times 0 to the 4th. Just plug in an upper bound minus lower bound like normal. And now we simplify. 3 to the 4th is 81 times 3, I believe, is 243 fourths. This is 0. That's your answer. So when you do u substitution and you have a definite integral, numbers in your bounds or your limits of your integral, do the normal u substitution. That doesn't change, but you must exchange your x values for u values using your u substitution translation. That's it. And of course, I'll have some in the practice exercises as well. Now, what we're going to go into here is something that some people cover and some people don't. I'm going to go over some very basic simple properties. That is, what happens when you have definite integrals of even and odd functions? And I include this in here because this is, again, definite integrals. It sometimes comes up nicely with u substitution. It rounds out your definite integral understanding. So I'll put this as like a bonus material at the end of this video. How about that? So with this, anytime I've got an odd function, so f of x is an odd function, meaning you're symmetric about the y-axis, not the y-axis, about the origin. You're symmetric about the origin. Here we go. Right? You get the flip on both sides, symmetric about the origin. If you have bounds that are opposites of each other, the area will be 0. So in this case, I've got x cubed minus x. That's this function right here that's been graphed. Notice that it is an odd function. So if you happen to notice this stuff, and you're bounded from a -1 to a 1. So if you happen to notice this stuff, great. If not, a lot of teachers skip over this, but I want you to have this in your calculus arsenal. So from -1 to 1, you have the same amount of positive area as you do negative area on the other side. Thus, you're going to end up getting 0 as your answer. That's a quick shortcut, but you have to notice that this thing is indeed odd. Okay, on to the next one. If you got an odd function, we've got an even function. Well, here we've got an even function. So an even function is one that is symmetric about the y-axis. If you have opposite lower bound to opposite upper bound, like this, that's the same as saying 2 times the integral from 0 to a of f of x dx. And I'll show you this in action. So here you've got plain old x squared, a very typical even function. We're integrating from -2 to 2. So because of the symmetry about the y-axis, and I'll show you that symmetry, this area here is the same as this area right here, the same exact thing. So instead of integrating from -2 to 2, we could just say, let's integrate from 0 to 2, like so, and then double the answer that we get. The convenience of that comes in the fact that integrating with a base of 0 is much easier than integrating usually with a base value of anything but 0. So again, 2 quick things to notice. I throw that in there at the end of all of our integration problems. It's not technically U-substitution, but it's nice little bonus thoughts that are often thrown in at this point in the curriculum. All right, that's it. I hope you had fun on this one. Peace.